Hi, I'd like to work through computing the derivative of this arc cosine function and I want to get an algebraic expression for the derivative, not just in terms of sines and cosines, but in terms of just a plain old algebraic expression of the variable x. So we want to compute d dx of arc cosine of x, and just in terms of basic functions, we don't have a plain expression for how to take the derivative of that. It's not 1 over cosine, it's arc cosine, the function that undoes taking cosine. So the key insight to being able to compute this derivative is to rewrite it in terms of just a plain old function like that. And then I'm going to take cosine of both sides of this expression so that I'm going to have cosine of y equals, well, the reason I'm taking cosine is that it's the inverse function of the arc cosine function. So I'm just going to end up with just plain x on the right-hand side. And now I've got plain trigonometric function and just a linear function of x on the right-hand side, and I know how to take the derivative of this. So let's take d dx of both sides. The derivative of x with respect to x is just 1. And the derivative of cosine of y is minus sine of y. And then I have to chain out the derivative of the inside, which is y prime, or dy dx, depending on how you're feeling about your notation today. And finally, we can isolate y prime by going and dividing by this sine of y, so that y prime is equal to 1 over minus, I'm going to put the minus sign on top, sine of y. And then finally, I can substitute my identity for y back into this expression to get y prime is equal to minus 1 over sine of the arc cosine of x, which is a modestly dissatisfying expression because I'm going to undo a cosine function and then I'm going to do a sine to that, which is in particular, it's easy to forget about the domain of this function, namely that x is supposed to live between minus 1 and 1, because it's supposed to be a valid output value from the arc cosine function. So let me erase some of my extra notation on this right here. Yeah, we took derivatives. Thank you. Okay, so this expression right here is going to help us lead the way forward. So cosine of y is equal to x. So I've inscribed a little right angle inside of a unit circle. So the unit circle has radius 1, so I'm putting a 1 right there. And we want cosine of y to be x. So I'm going to label one of these two sides here as x, and the other one is going to be the complement in the Pythagorean theorem with respect to that number. So the cosine of this angle, which we're calling y, the cosine of the angle is x. So, ka, toa, so sine is opposite over opposite over hypotenuse, ka, adjacent over hypotenuse. So I want adjacent over hypotenuse, so I want that to be over hypotenuse. The hypotenuse is 1, right? Here's the hypotenuse. So this is going to be adjacent over hypotenuse. So that leg right there is going to be x in this triangle. And then the other leg is going to be the complement in the Pythagorean theorem. So that the two side lengths, 1 squared and summed, give you 1. So the right thing to put right here is the square root of 1 minus x squared. That is totally off camera. Ta-da! It's on camera now. Okay. So we're gonna rewrite this in terms of this thing right here. So right, y prime is minus 1 over sine y. Well, here's y. So now instead of doing this thing to it, we're just going to read off what this expression right here, sine y, is supposed to be from our unit circle diagram. So this is going to be minus 1 over let's see here. So y is this angle. We want sine of the angle. So opposite over hypotenuse. So that's going to be the square root of 1 minus x squared. Is, I think, the world's worst square root symbol. But I'm going to let it go. So y prime is minus 1 over the square root of 1 minus x squared is exactly the same thing as this thing right here. So there are a bunch of identities for the arc trig functions. And they're all given in terms of, they have like these square roots here, and their derivations all follow this basic pattern where we're going to be like, no, I can't deal with this inverse trig function, so I'm going to move it back over onto the y. I'm going to do implicit differentiation. I'm going to solve for y and put it like this, and then I'm going to read off the thing that I'm supposed to put here from a unit circle flavored diagram. So rather than do all of those for you, let me instead summarize these all with the statement of the function and then its derivative. So we already know the one for the inverse cosine. So let me put its derivative back up top here. So we're going to have the inverse cosine, and its derivative is, so this is going to be f, and this is going to be f prime. Its derivative is minus 1 over the square root of 1 minus x squared. Sine inverse of x goes to, nope, those are not equal to each other. Brain, you had better not do that. I'm going to put a vertical bar so I don't, they're not equal. This one's 1 over the square root of 1 minus x squared, which is fascinating, so that their derivatives differ only by a minus sign. So you can remember both of those in one go really easily just by realizing that when you take derivative of regular cosine, you pick up a minus sign, right? Because the derivative of cosine is minus sine. So that'll help you remember. So these both have the same basic form. It's just that the cosine one has the negative sign. The next one is going to be the arctangent function. So the derivative of arctangent is 1 over x squared plus 1, which is, I mean, like, really? Like, we go from this inverse trig thing to this, like, simple ratio right here? Like, wow, that is just nuts to me. I'm going to do the other three in a table here and then hide in the corner. So let's do f prime and f. So let's do the other three. Since I did cosine, I'm going to do secant. So there's arcsecant, and its derivative is 1 over the absolute value of x times the square root of x squared minus 1. Let's do cosecant inverse, and then we'll do cotangent inverse of x. Okay, the derivative of cosecant inverse is minus 1 over the absolute value of the square root of x squared minus 1. So that's kind of nice because these two now differ only by a negative sign also. So just like you only have to remember essentially one formula for these, and the minus sign goes with the cosine, here the minus sign goes with the co. So that's not so bad. And then finally, the derivative of cotangent is minus 1 over x squared plus 1 is exactly minus what you would get from tangent. So you have about 3 formulas here to actually remember. In my opinion, there's the cosine sine pair, which differ by a minus sign. You have the tangent cotangent pair, which differ by a minus sign. And you have the secant cosecant pair, which differ by a minus sign. So if you can remember those 3 things, then you can remember all 6 of them. So pretty straightforward as far as that goes. Let's conclude by taking a derivative and doing the chain rule on it using one of these formulas right here. So let's say leave the tangent inverse one up, and let's do a derivative of a tangent inverse function. You know, it'll suffice. I'm just doing this off the top of my head. It'll suffice to do, I think, an arc cosine, and you'll see how it goes. So since that one's at the top, I'm going to do it so I have less erasing and rewriting to go. Okay, so we have f is the arc cosine of x, and then f prime is that. So using the chain rule, my friends, we can now take the derivative of expressions involving arc cosine just by using that formula. So let's take the derivative. Let's take dx of cosine inverse of e to the 2x. Perfectly reasonable thing. So this is the composition of functions, right? I've got this inside function right here. That's the inside. Fundamentally, this function that I'm taking the derivative looks like arc cosine of. And the derivative of arc cosine of is this thing right here. So this derivative is equal to minus 1 over the square root of 1 minus, and instead of x, I have this blob, e to the 2x, and that's squared. So I'm going to turn that 2 into a 4. That's a 4. Does it look like a 4? Yeah, it looks like a 4. Times, and now I have to chain out the derivative of the inside, 2 e to the 2x. Right? Not so bad. That is not so bad. So memorize 3 formulas, and you get 6 derivatives, and then an infinite number of them by applying the chain rule to it. And as usual, these functions can be combined into complicated expressions using chain, product, quotient rules, sums, differences, and all the different ways that we can make functions up to take derivatives of. So that's inverse trig functions in a nutshell. Thank you very much for watching, and I will catch you later. Bye.